Okay, I think we can start. Here we have, this is the 8th Clean Water Conference that URI has held. It's in combination with civil and chemical and a number of other organizations, including AICHE, participating. We have a very interesting program today. The first speaker will talk about what's required in the state and some other major issues in the state for tertiary treatment of wastewater. This is the third stage in treatment, and instead of going to 80 or so percent, a little more than 80% reduction in pollution, we can go to over 90% with that tertiary treatment. So the first speaker will represent the state and give the where we're going in the state. The second speaker will be talking about the new specific issues that they will try to put in a tertiary treatment into the Warwick Sewer Department. And the final speaker comes from East Greenwich and will give the way East Greenwich deals with tertiary treatment. And East Greenwich has been dealing with tertiary treatment for a number of years at this point. And maybe we'll hear that they've added some additional things to tertiary treatment of wastewater. Almost all the wastewater eventually ends up in the bay, and so there's major reasons to make sure that the water gets cleaned up.
I'm on there for welcome, so
Go ahead.
Thank you. I'm really proud. I'm the director of the Rhode Island Water Resources Center, and the center has funded Harry's program for 8 years now, which is a long time. But this program, which is a long time, but we've had some excellent speakers. So I see a lot of people here that I recognize. Angela is an alum of civil and environmental engineering, the first speaker. So I'm looking forward to a great conference here. So Harry, take it away.
Okay, so we partially introduce Angelo Liberti. He's the director of the Rhode Island, in Rhode Island DEM of Water Resources. And I think I mangled the title a little bit, but he's the person, the important person in the state to make sure this happens. He is a graduate of civil and environmental engineering, and we're proud of that. And so without anything further, we'll let you come up and tell us all about the world here. No, it's not.
What's that?
Oh, there you go. Kimmy saved us again. Yeah.
Yes, that's right.
Okay, thanks.
Good afternoon, everyone. I'm guessing it must be required that you come as part of your classes, because it's a pretty good turnout here, but appreciate it. And as you mentioned, I am a graduate of the master's program in civil environmental engineering. I worked with Ray Wright on water quality modeling on the Patuxent River, turned into an internship, and turned into a 26-year job with DEM. And sometimes I curse him for that, but generally it's a pretty good job. I can't complain. I wanted to take a minute. My title is Chief of Surface Water Protection in the Office of Water Resources. Pretty much I have all programs that involve surface waters except the on-site program, which is basically a groundwater program but interacts with surface water, the wetlands program, and the on-site wastewater treatment. So everything from setting water quality standards, evaluating if water bodies are meeting the standards, opening and closing shellfish areas, writing permits for wastewater treatment plants, doing design reviews of wastewater treatment plants, financing, operation and maintenance. Art Siemens here with me today. He's also a graduate of civil environmental engineering. His responsibility is basically to review the engineering designs. And so I figured if we have any tough questions when I get to that part, I can point over to Art. I just wanted to quickly sort of orient everybody here. So these different drainage basins all come into Narragansett Bay. The upper one is for the Blackstone River up in Massachusetts, comes down through Woonsocket into Providence. And this is the Mount Hope Bay drainage area coming into Mount Hope Bay here. The upper Providence River, so where 195 crosses the hurricane barrier, the new bridge of Providence, is kind of the start of the Providence estuary. Off over here is the Seekonk River that goes up towards the new 95 bridge that crosses in Pawtucket as the start of that estuarine portion. So these two come together into the Providence River. This is Communication Point here, and the Patuxent River flows northward towards into the Providence River. So what's happened in a lot of New England is we sort of put our urban centers in the worst possible places. So we have Worcester at the head of what is a little tiny tributary at that point to the Blackstone River. It's not very wide, it's not very deep, there's not much flow. Then we add some other cities, and then we come down into Providence. Pawtucket, and same thing, comes down, and so we dump a lot of nutrients from our municipal wastewater treatment. Rhode Island's a little unique because we don't have a lot of direct industrial discharges. Most of the industrial discharges in the state go into the sewer, into a municipal treatment plant. So usually when we're talking about the water pollution and point sources, we're talking about municipalities, which means taxpayers and municipal wastewater treatment plants, not some big company that's perceived to have deep pockets that can come in and correct the situation. So basically I wanted to talk about how we're regulating point sources and give you a quick overview. The way the federal rules are set up, there are technology-based standards, and those are basically straightforward standards. If you're a municipal treatment plant, you have to meet this standard, period. The most common one is called secondary treatment, and there actually was a waiver allowed. The point of secondary treatment was to get out the major carbon, major solids, and it was set as a baseline across the country. Back in the mid-'80s, Newport actually applied for an available waiver so they wouldn't have to do secondary treatment. They wanted to see if they could keep doing primary, just settling, disinfection, discharge, right around the Newport Bridge. But that was denied by EPA, and they had to upgrade to secondary, which kind of surprising to me when I think back. Here we are in the early 80s, and we're still thinking maybe primary treatment's all right at one facility and all that. So, look, I'm not sure. How am I doing this? Yeah, I didn't think so, but uh-oh.
Just press the back arrow.
Sorry. Okay, so in addition to this federal standard, you can also, at a state level, set technology-based standards based on what's called best professional judgment. I'll talk about that a little more as we go along. And the toughest part, which is kind of exactly when I joined the department, was water quality-based limits. Now you have to look at each facility and decide, is secondary treatment enough to meet the water quality that's necessary to support swimming and fishing and other aquatic-like uses. And if not, you need to issue a permit limit that will allow the plant to achieve those uses. Those can be anything from simple dilution calculations to complex water quality models. And one term you may have heard about is a TMDL. If a water body is impaired, a state has to put it on a list, say it's not meeting the standards, and come up with a schedule to come up with a plan on how it would achieve standards, which is kind of interesting compared to some of the other environmental programs. So we need to put this list out there, evaluate all the state waters, and then let people know on a 20-year plan how fast we think we're going to be able to come up with these reduction plans. Seems to get old. I'm sorry. I don't know how I got to
Got it, the back arrow?
Well, that's what I thought I hit. That didn't work.
Oh. You got it?
Yeah. That's it. Okay. Sorry.
Use timing is clips up there, see? Keep going to the right. Yeah, I would unclip that.
No, I didn't think there was a mouse there. What the heck am I doing?
Can I ask you a question?
Sure.
You were saying that in Rhode Island, the industries go to the treatment plant, and then, so those are your point sources, the treatment plants.
Yeah.
But are those industries in a pre-treatment program, and who regulates the level for the pre-treatment program?
Yeah, sorry, good point. I should have mentioned that. Yeah, the industries are required to reduce their loadings to a level that will protect the plant. So it can't interfere with the treatment process of the plant, it can't cause problems in the sewer system, and it can't go through the plant and cause a violation. And for the most part, that authority is delegated to the local level. So whoever's in charge of the treatment plant is in charge of setting those standards, enforcing it, doing the monitoring. Just wanted to give you a quick idea. So once we decide that we need to reduce permits beyond secondary, we come up with a draft permit. It goes through a public comment period. And because in Rhode Island, we're not authorized to have schedules inside the permit, we're issuing permits 90% of the time that we know people cannot achieve. They never like that. They never understand that. But that's how we get water quality improvements. We issue something that they can't currently attain. They have to appeal it, and we enter a consent agreement if both parties agree with a schedule to go forward with facility planning, design, and construction. In my experience, it's really interesting. When you get the public comments, most of those are, DEM wouldn't know science if it bit them in the butt. What are you making us do this for? There's no evidence necessary. And then the transformation occurs when you get to the ribbon cutting, and then this was all the community's idea. This great, wonderful foresight that they had to protect the bay and protect the resources, but that's part of the job, so I won't complain anymore. Oh my God. The main water quality issues, and there are others, but I wanted to stick to whether it's on a river or bay, dissolved oxygen is the main one. We also have different aquatic toxicity, but metals and things are mostly dealt with through pretreatment. Ammonia is really the big one that's dealt with by the municipal plants. And whether it's saltwater or freshwater, excessive algae growth, rivers, it's usually attached algae. The bay, it's usually phytoplankton. So the federal technology standards we talked about earlier are pretty straightforward, just the biochemical oxygen demand, TSS. These are the nationwide standards. Water quality regs, we have some narrative standards about having to further treat phosphorus. But generally, when it comes to nitrogen in the bay, there's not a standard for nitrogen. It's how it relates to the nitrogen cycle, phosphorus growth, and dissolved oxygen. We adopted a few years ago a fairly complex dissolved oxygen criteria for estuarine waters. It used to be a straightforward value that it couldn't fall below 5 at any time. Actually, the EPA lab in Narragansett took the lead on developing more sophisticated criteria so that you could have dips below a certain level, as long as it didn't stay low too long to be harmful to aquatic life. So that really necessitated being able to monitor oxygen on a continuous basis so we could compare it to these standards. So a system of buoys was set up around the bay with the help of some other partners, the Narragansett Bay Commission, URI. This shows the location of the buoys, and the worst parts of the bay are colored in how many days it's typically not meeting water quality standards. And so this is the Seekonk River that I mentioned earlier. The Blackstone dumps into that, the 10-mile river. This is about the hurricane barrier. The Fields Point wastewater treatment plant is up here. Buckland Point, NBC's Buckland Point is there. So this upper part of the bay has significant oxygen problems, as does Greenwich Bay. One thing that is pretty obvious and has been generally accepted, the bay acts as sort of two different bays. The lower part of the bay is fine. You know, we don't see any issues with excessive nitrogen or low oxygen. But in the upper part of the bay, we do. And it's generally been accepted that what happens is this high nutrient, low DO water is what comes down and affects this part of the bay. And the general agreement that if we solve the problem here, these issues are going to be resolved based on the location of the sources and the dynamics going on. One thing is, back in 2003, there was a major fish kill in Greenwich Bay. That got a lot of people's attention and got people focused on something that the department, URI, a bunch of other research has been working on for decades. So I just grabbed a couple of quotes back from '79 and '80s that people knew that oxygen was a problem, and we were working on it. The fish kill in Greenwich Bay was just a combination of bad events all at the same time. The environmental conditions that occurred at the time, the fish were there, the oxygen quickly dropped, they couldn't get out of there, and large amounts of menhaden died in that event. But there had been earlier events of other species as well. So we've been trying for a long time to model the bay. We being a bunch of different researchers from EPA and Applied Science Associates here in Narragansett. But we weren't able to come up with a model that we thought was successfully calibrated. Phytoplankton blooms happen quickly, they vary in space and time. It's difficult to get the three-dimensional water quality modeling accurately calibrated to be able to come up with a reduction plan. So what we ended up doing was looking at these experiments done down at the Graduate School of Oceanography. They had large tanks that they dosed with different amounts of nitrogen and measured various response variables. They looked at chlorophyll, dissolved oxygen, a few other issues. And the way that they dosed them was to look at X number of times the average surface loading of nitrogen. So they took the bay and said it has an average surface loading of, let's say, 10 pounds per day, just for a number. And if it was 20, then that was a 2x loading condition. So it's the number of times compared to the average. So, for example, they plotted up this curve of if you're 16 times the average, then the oxygen level is expected to be around 2. So we use that and some other information to look at what would we be able to achieve in various parts of the upper bay if we were to reduce the load. So the Seekonk River, that was the smallest river up to the right, Route 95 down into Providence. And you can see that we started at a very high existing condition. And what we were looking at was jumps in technology. We had 11 facilities that we threw into this analysis, and we looked at reducing them to 8 milligrams per liter, 5 milligrams per liter, and 3. And given the scientific uncertainty of this analysis and the modeling that wasn't too successful, we were trying to find a break point where we thought we were reducing the loading factor to a reasonable point that we should see some worthwhile response and not spending too much money. So we ended up coming up with this option where the largest treatment plants in the upper worst locations were to reduce to 5 milligrams per liter, and some of the others were to reduce to 8. But you can see as you go, the Seekonk River would still remain in a higher loaded condition than a little further down to the Fields Point Reach, and then this is about halfway down the Providence River. So in the end, the plan that was put together was that there would be about a 50% reduction from Rhode Island treatment plants. And each treatment plant has a design flow. They have to look 20 years out to the future and see where they think their population and if they're going to expand their sewer system. And so we're going to be sliding backwards a little bit. So it's going to start out around a 65% reduction, sliding back to 50%. We've been working with Massachusetts and EPA to get comparable reductions from the Mass facilities that are important. And overall, we think it'll be about a 30% reduction in total loading. Most of the studies agree that about 70% of the total loading of nitrogen to the upper bay is coming from wastewater treatment plants.
What about stormwater utilities?
Stormwater is part of the other 30%, but 70%, the estimates have been from like 65 to 70 coming from point sources. And when you look at some of those studies, you have to be careful because some looked at rivers and they called the loading from rivers versus the loading from treatment plants. But on the incorporated in the river was significant loadings from the treatment plants. So when we did our estimate and others did, we tried to extract the wastewater treatment plants from the rivers and put them in with the wastewater treatment plants. Actually, I should have been asking as we go along. If there's any questions, feel free to ask. Sorry. So there are 11 facilities in Rhode Island. I put in yellow the facilities in Massachusetts. Upper Blackstone is the largest. That's the one that's in Worcester. It's at the head of the Blackstone River. North Attleboro and Attleboro are on the 10-mile river. So the three of those all end up in the Seekonk River. And and Grafton, Uxbridge, and Northbridge are also on the Blackstone River. They've all been issued permits. Upper Blackstone is basically in compliance. I believe Attleboro is too, and North Attleboro is working on it. All the Rhode Island facilities, the largest ones, Woonsocket, Fields Point, Buckner Point, were issued 5 milligrams per liter, and East Greenwich was issued a limit of 5. With all of these facilities, there was a concern that we may have to go lower in the future. Based on the analysis we did, it still looked like we might not quite get there. So we always tell people when you're doing your planning, make sure that you can add on additional treatment if you need to. You don't want to build a tank 2 years later, take it down. So everybody's done that. When Woonsocket was looking at that, they had already been through one upgrade. They didn't want to go through another. So they decided to just make this second upgrade for 3 milligrams per liter. That was a difficult local decision. People were pushing on both sides. Why are we going further than we need to? But they really felt that the writing was enough on the wall and the delta in cost was not worth only meeting the permit limit of 5. So we've been trying to estimate the schedule that we think we're going to get this done. And every few years, this schedule drags out a little more due to a whole variety of factors between, Warwick talked about, the plant getting flooded. And you'll hear about that, I'm sure, later on. So they needed some additional time just to deal with that, get the plant back into running condition. Woonsocket's had some significant financial problems, and they came to us and asked to spread out the schedule some more. So this was our best estimate of originally how in 2005 we thought we'd be all buttoned up by 2011, estimating how long it would take to settle the appeals, enter a schedule, get the planning, design, and construction. I always did this graph by holding the flows constant because I just didn't want to introduce year to year. Some of these plants have significant changes in flow, and I thought it would skew where we were really. So all of these initial and then actual were based on keeping the flows equal to what they were in 95, 96, and just changing the concentrations to the permit limits. But in 2011, we decided to use actual data and see how close we were. So I was really happy to see that it actually matched very closely. So the actual flows and actual concentrations were right in line. Since 2011, Fields Point came online a little early, so they were actually meeting in 2013, and Fields and Buckland are on, Buckland's on schedule to finish, so we will definitely be at that point in next summer. I quickly mentioned earlier the Massachusetts permits. One thing I wanted to point out here, and it's something we heard again last night. We were at a hearing for the Warwick City Council on approving two bond issues, one to upgrade the treatment plant and the other to extend sewers. And one of the public comments was, you should have fought this when you filed your appeal. Look at all these things you said DEM did wrong. Why did you go ahead and settle it? Let's fight them again. Well, the Upper Blackstone treatment plant in Worcester decided to keep their appeal to the end. So they went through, the first thing they do when EPA issues a permit is you go to the Environmental Appeals Board, you follow that with the First Circuit Court if you want to, and then you try to go to the U.S. Supreme Court. So they went all the way to the U.S. Supreme Court and they refused to hear it. So now they're stuck with the limits and they paid a lot of money on their legal costs, technical costs to get there. Wanted to talk a little bit about some of the technologies that have been selected. Basically, for nitrogen removal, it's all an enhanced biological process, trying to get the nitrifying bacteria that break down the ammonia to thrive in one section of the tank, and trying to get denitrifying criteria, so bacteria to take over, so you can strip the oxygen, drive off the nitrogens. So there are most people that had the lower limits went with a 4-stage Barton-Faux process. A couple have added this IFAS media. It's basically media added to the tank, so you have more surface area, so you can get more biological growth within the same footprint of the tank. So that way they don't have to build additional tankage to get the same amount of production. So real quickly, an MLE process is basically the first two tanks of this, where the waste comes in, it goes into an anoxic zone, and then followed by an aerobic zone with a recycle. They had a second process to be able to further reduce nitrogen down, so that they could get, generally the first stage can get somewhere around 8 to 10, and the second stage can get them down into the 3 milligrams per liter, so 5 milligrams per liter, followed by clarification. This is a couple of pictures of that IFAS media that gets added into the tanks to enhance the surface area. This one's showing a little bit of growth inside at these spots. It was kind of interesting, a few years back, a bunch of this washed up on Block Island. There were some plants in, I think it was New Hampshire, actually, that had excessive flows into the plant and it washed the media out. There are screens that are supposed to keep that in the tank, but it got washed up and over. And a couple of facilities in Rhode Island have tried to learn from that and design for it, and hopefully we won't see that stuff showing up on the shoreline. Here's another manufacturer's where it's more like a thin screen type idea, and you can see some of the other ones in the background there. The city of Woonsocket went with a slightly different process. It's a 2-stage activated sludge. What they explained that they were trying to accomplish here was to have a smaller retention time and deal with high-strength carbon waste, and then have a second series of tanks, the same basic series of tanks, to further reduce nitrogen before it's discharged. Now, they have an existing filter that they're going to continue to use, and they're going to do chemical treatment for phosphorus removal because they're on the Blackstone River, so they also have a phosphorus removal requirement. So the next step when it comes to nitrogen is to finish up construction. The last facility is supposed to be online in 2017, but basically we're very close to the the load reduction that we were planning for. The buoy system in the bay is going to continue, and we're going to keep monitoring the changes in oxygen. There is a group at the Graduate School of Oceanography, got a multi-year grant from NOAA to work together on trying a slightly different approach to modeling, to do a bigger box model. They're doing a complex hydrodynamic model, 3 dimensions, but they're using that to drive 20-cell for the entire bay box model. And they're going for a more simplified representation of the reactions. So looking at the major phytoplankton growth, nitrogen cycle, but some of the EPA models, you can get down into the sediment. The sediment can have 5 layers. Each layer can have an interaction term, and you start getting to the point where you got to make stuff up because you can't measure it. You can't measure how much nitrogen moves between layer 1 and layer 2 at what rate per day. So there's always an art in modeling to try to make sure you're capturing all the major important processes at the right scale, but having enough data to calibrate those equations properly. So they're taking another look at that. Meanwhile, the EPA lab just embarked on trying to do the more sophisticated 3-dimensional stoichiometric type of model again. There's been a lot of hydrodynamic data collected in the last few years, and that was the big problem with trying to do the more sophisticated modeling was getting the hydrodynamics right. So hopefully, between these 2 efforts that are going on, we'll end up with a tool that most people can agree is a good representation, and we can see if we still need further reductions, where should those reductions come from, and how low should they be. And so we're still waiting to see what happens with that. In freshwaters, there's a couple of criteria about phosphorus, and most of our treatment plants are to rivers, and they may have impounded areas that could or could not react to the pond. But we don't really have any municipal treatment plants discharging into ponds per se. So we normally take a look at the retention time and decide whether or not we think that this impounded area is really reacting to phosphorus the way a lake or a pond would. And we have a numeric standard of 25. EPA recommends 100 micrograms per liter for a flowing river. And in 2000, EPA came out with a recommended guideline, which is about 24 micrograms per liter. And states are not required to adopt that, but EPA's been pushing the states to develop it right here.
Could you explain to me what a kettle pole is?
Not really. Sorry.
That's right.
I'll be honest. I think it's a glacial depression that was left, and somebody else could fill me in. Hey, I appreciate help. Thanks. And I think it was usually near the coast, or not necessarily. No. Any other questions? So we haven't really embarked on trying to come up with a new phosphorus criteria for rivers. We're focusing on lakes and ponds right now, and we're right now assimilating all the data, trying to see how ponds and lakes in Rhode Island have reacted to different concentrations. Just want to point out real quickly, this is on the Patuxent River, and that flows up into the mid part of the Providence River. And West Warwick and Cranston are all, I think, within a 5 river mile stretch. And it's just another kind of example of where we put things in bad places sometimes. And so there was a huge amount of loading going into this stretch of the river. And back when I was working at URI, at the end of this river, there would be no oxygen in summertime, 0. And when we first came out with permits saying that we need to bring this river back and get oxygen back in the river, letters came from all the mayors, meetings with the governor, change the classification, make it waste assimilation. This river is never going to be good for anything. And this was in the early 90s. And actually, we went ahead with the modeling. We showed that we thought if we knocked down ammonia, we'd be able to meet oxygen. And luckily, this is one of the big success stories that we're now meeting the oxygen standard at the end of the river and throughout the river. So we've taken it off the impaired waters list for oxygen impairments. However, we still have areas of excessive plant growth in the river due to phosphorus. That was something we thought was going to be a problem. We mentioned it back in the 90s, but we didn't have a model that would predict the change in growth based on changes in phosphorus loading. So we kind of just left it originally with, this is going to be an issue, you should think about it during your design for a moment. These are all the facilities in Rhode Island that are on rivers that have to worry about phosphorus. So at this point, we don't have any other plants that we think need to be assessed for their phosphorus limits. And there we've gone with a limit of 1 in the wintertime and 0.1 in the summertime. 0.1 is kind of a combination of the generally accepted best technology. People can do lower than that, but it's generally been accepted that that's a limit of technology. And it can, in each of these cases, we believe, meet water quality standards. We did give Smithfield a slightly higher number based on the characteristics of their receiving water. We thought that they would be able to not have excessive algae growth. The reason for the limit in the wintertime was to make sure that we don't have phosphorus sediments behind the dam accumulating and becoming a problem in the summertime during the growing season. I forgot to mention that right now we're limiting nitrogen only in the summertime for the wastewater treatment plants. The general belief is that the loadings that we're seeing in the winter are flushed from the bay and don't return in significant amounts to be a concern. But we've written all the permits to say that you should operate your system year-round to the best of your ability, but not to do carbon addition. So some people are doing carbon addition in the summer to make sure they can get low nitrogen. We're just not requiring that piece of it.
That looks like a lot of construction in Rhode Island that's coming up. Is that right?
Yeah, actually, a lot of it's either underway or coming up soon. So yeah.
So what does that represent? 200 or 300 million?
Probably not that. Well, almost. Let's see. Everybody is doing nitrogen and phosphorus, I think, was on this list. Smithfield has already done the nitrogen part, and they're just fine-tuning. I think Woonsocket was maybe in the $20 million range.
30 million.
30. And AR, you want to answer this question? Do you know?
Roughly about 150 million if you add it all up, not including Smithfield, which is going to be done in the spring.
Between the phosphorus and the nitrogen, or the?
Yeah, Bonneville, we don't know what their price tag is, but assuming it's in the $10 to $20 million range.
Hi. I'm really sorry to interrupt, but is there a lost ID in the last row at all for Captain Lyons? I think I left it. Yep, it is.
So that's 6 of the 11 plants. Are the other 5 plants, Westerly?
Yeah, Westerly is complete. Warren is doing planning right now for nitrogen removal. That's due at the end of the year. So this slide is just the phosphorus side of things.
And Providence is okay?
They're finishing construction. Fields Point is already finished. Buckland Point is finishing, and in the spring has to meet their limits.
There's no phosphorus for them.
No phosphorus, but for the nitrogen side, yes. Most of the facilities have gone with ballasted flocculation as the preferred treatment alternative. And basically what that is a chemical addition process, but the main feature is that something is introduced, a fine sand, to make the chemical flock settle faster. So in a small area, again, similar to sort of IFAS, but a different process. You know, here it's a chemical physical reaction, and the sand is added to make it settle faster. So that way you don't need a big clarifier where you have a long time for the particles to settle out. And then it comes in to a settling tank, and it goes to separation. So you physically separate the sand from the chemical flock, so you can reuse the sand again, put it back into the process. And this has been used in quite a few places and it's highly efficient and allows the phosphorus to be removed in a pretty small footprint. Sorry, probably going fast. Is there any other questions about what I presented or anything else in general about water quality in the state?
I have a question about the phosphorus removal. Why are you using chemical removal? Most places are going with biological now.
I should have mentioned, Woonsocket is doing a combination of biological and physical. And I think most of the treatment plants are getting some biological removal up front in the plant, but to get down to the limit of 0.1, they need to polish it off with some kind of chemical treatment.
That creates a lot of sludge.
Yep. Yeah, that's been a concern that, we only had 2 facilities in the state that are doing composting of municipal sludge, and one is on its way out or considering dropping it completely, I guess. But yeah, that would be a great thing to be able to reuse this phosphorus as something beneficial that's being removed from the plants.
Geologic, whatever survey, they do measurements on the rivers
Yeah.
in the bay. Do they measure phosphorus or on?
Yep. They measure it usually on the major rivers. I think it's monthly, I believe. And so various researchers have looked at those loadings to come up with the estimates of wastewater treatment plants versus non-wastewater.
And did you measure the DNA of the?
No, he's giving me a hard time because I was at a public meeting getting kind of slammed for in Greenwich Bay, why are we going towards sewering and replacing of cesspools when there's all kinds of wildlife out there introducing bacteria, and we could do a DNA test to decide that. And I mean, it's definitely a valid concern that that urban stormwater carries large amounts of bacteria from animals. And there's no distinguishing in the water quality standard, whether it's the standard for safe shell fishing or for swimming. If the fecal coliform is there, it doesn't matter if it came from a duck, a goose, whatever, it still has to be closed to shellfish. So we need to take care of both of those issues. But you know, our point, we've done a little bit of that testing. Sometimes it's inconclusive, but we always came up with a human signal, and you still need to deal with a human signal. So, you know, our response has been, we really haven't spent a lot of time doing that. We've used it sometimes, not DNA, but other markers to track down when we find a pipe, is it human or not. But in facility planning, they look at an area, they look at the soil types, density of the housing, depth of groundwater, history of repairs, and decide, should this area be sewered or should it be, can it stay with on-site systems? And what happens in most cases, the housing is there. You would never build that housing today, and you wouldn't be allowed to build that today with an on-site system because their lots are too small, the houses are too close together, but they're there. And people come to the department when their system fails and say, I need to do something. Well, if sewers aren't there, we don't kick them out. We come up with the best solution we can get to fit on their property for them. And that often gets misconstrued to be, why do we need sewers then? Because you gave me a permit, you must think I did a great thing. And it's like, well, we think you did a good enough thing to solve the problem that you have today, but we don't think it's a long-term solution in some areas.
Okay, any more questions? Let's thank our speaker. Okay, Leon, do you have anything? No coffee, no? It's over here? Okay, we'll take a break, come back at 2. Lemonade, cookies, coffee.
specificity, it seems like
Took some of my courses when she was here, and we're proud to have her make a presentation on tertiary treatment includes the advanced nutrient project, just as we heard from the previous speaker. Thank you for coming.
Thank you. So as Professor Nichols said, I am a graduate of URI's chemical engineering department, but I haven't practiced engineering in probably 15 years. I'm more of a manager at this point. So I'm going to speak about the upgrades that we're going to be undertaking in Warwick from a project management point of view. And Angelo was with me last night before the city council, and we secured a vote, 7-2 vote for bond authorization, so we're actually going to be able to start constructing this project early next year. But the original treatment facility, which is shown in the aerial in the back, was constructed in 1965 on the banks of the Patuxent River. We had a couple of major upgrades, 1982 and 2004. And we have about almost $250,000 invested in wastewater infrastructure in Warwick. I manage a $21 million budget. Our treatment facility has 7.7 million gallons per day treatment capacity. And we have a 24/7 operation. I have 30 employees and almost 22,000 customers. Not sure if you can see, oh yeah, you can see it. All right, so here's, again, an aerial of the existing plant as it is today. And just want to point out a few of these process units. So we actually have a 48-inch line that comes, the influent pipe that comes under Route 95. So that's something that keeps me up at night. To the headworks, which is basically what we call preliminary screening. Large objects get removed. Anything you can flush down the toilet, throw in a manhole, we see it at the treatment plant, and it gets taken out at the headworks. The primary clarifiers are basically just big settling tanks. Probably remove, I don't know, 60% of the solids at this point. Anything heavier than water will sink to the bottom. Anything lighter will float to the top. Next, we have a biological nutrient removal system, an aeration system, and that's really the focus of the upgrade, so I'll speak to that. And then secondary clarification, again, once it's gone through the biological process, we settle out the solids, and it's pretty clear at that point, and really just have to hit it with a little bit of chlorine to get rid of the remaining fecal matter bacteria, and then throw another chemical in there to make sure the chlorine levels are right, and then we discharge it to the Patuxent River. Professor Nickel wanted me to make sure I tell you nitrogen and phosphorus, the nutrients that we're dealing with. I mean, these are naturally occurring substances, chemicals, and nitrogen in particular is naturally occurring. It's urea, the stuff we deal with every day is chock full of nitrogen, so. Let's move ahead here.
Do you have a high INI?
We've been working at INI is inflow and infiltration, sources of stormwater basically, or other water that you don't really need to be treating at a treatment facility. But we have an aggressive program. Out of our average 5 million gallons a day flow, I'm going to say we have about 200,000 gallons a day in II.
How is it being affected right now with the drought we're in?
Our flows have been pretty steady, around 5 million. We see that more when it rains, so the flows go down. Even with more new customers coming online, we're seeing flows go down, which is interesting, but I think a direct result of water conservation, low flow toilets, all that kind of stuff that's going on in the real world. So just briefly to compare some of the current effluent standards for wastewater treatment facilities, the biological oxygen demand and total suspended solids, those are traditional primary treatment standards that date way back. You can see what those are. And a removal efficiency requirement. There are pH standards, and again, across the country, what we're seeing for nitrogen, as Angelo mentioned, was discharge limits of 3 milligrams per liter to 10 milligrams per liter, and for phosphorus, 0.1 to 1 milligram per liter. And again, those are technology-based, available technology kinds of standards that they can absolutely get to. In Warwick, you can see we do pretty well on the main pollutants, and we do pretty well on the nutrient removal as well. Right now, we're averaging 0.6 milligrams per liter, maybe a little bit less of phosphorus using our biological process. Unfortunately, it's not low enough. So let me just talk a little bit about how we ended up in this big construction project. Angelo mentioned the fish kills, the algae in the river, a lot of the reasons why the Department of Environmental Management is looking at nutrients and trying to remove any additional sources. So, the joke in our business is they call us point sources because they can point to us and tell us what to do. But it's absolutely easier to control points, to manage point source pollution than it is to deal with some of these stormwater issues. Although I see more of a focus on that, and I do think that's will be worked on, and not so much the point sources. But so we got a new permit. It was like my first month on the job in Warwick, 2008, and the new limits were 8 milligrams per liter for nitrogen, which isn't actually that bad, and 0.1 milligrams per liter for phosphorus. But we knew in speaking with DEM that probably need to be looking at even lower limits, 5 milligrams per liter for nitrogen, and we were actually getting down to the water quality standards to see if we could get down to 0.023 milligrams per liter on phosphorus. We spent a great deal of time, over a year and a half, appealing this through legal mechanisms, and we decided in the end that the cost of continuing to fight it, we probably end up losing, as Angelo mentioned, that one of the cases recently went all the way to the Supreme Court and they declined to hear it, so I think they spent like $5 million appealing that, and that's money we could have put into construction or engineering, paid some of you guys. So we did sign a consent agreement in November of 2009, which basically set out a schedule we need to comply with to construct these improvements. So what we did, we put out a bid, qualifications-based bid for an engineering company to come in and help us wade our way through this process, figure out what we need to do to comply with our permit in the time frame that DEM set out. We hired an AECOM, and by the way, there's going to be some slides here courtesy of AECOM, and they wanted me to mention to you all that they are hiring. So if you go on to aecom.com, it's a great company. I enjoyed working with them, and if somebody's looking for a job, it's a great company, so check it out. And then we began working on a facilities plan, which Angelo spoke to. It's a 20-year plan. What are we going to do? What are we going to need for improvements in our collection system and at our treatment facility? As Angelo also, yes.
What do you project for growth in population or growth in sewers?
Yeah, so in Warwick, right now we have about 60 or 65% of the city's sewer. In 20 years, we'll be right up around our capacity at 7.7 million gallons per day. If we finish all of it, we have 10 more construction projects. We're probably going to bring on another 10,000 customers in the next 20 years. So that's our plan. Unfortunately, work started out a little bit later than everyone else, and playing catch up. And it's not fun being the last utility to put a pipe in the ground. It's a little complicated. Anyhow, in March 2010, my treatment facility was completely wiped out, underwater, 6 feet of water in my office. And so DEM felt bad for us. They gave us another year's extension on this whole facilities planning process. But just for your information, I took this photo. I got to go up in a helicopter with the mayor, which was pretty cool. But $14 million in damages. You can see no cars on the highway. That whole section of the highway was shut down back then, and every treatment tank, every process, everything had to be pumped out, dried out, reworked, replaced, electrical wires, everything. We had about $14 million in damages, but we were amazingly back in compliance with all our permits, including the nutrient limits, in about 3 months. And again, we had a lot of help on the engineering side from AECOM. They, right away, they weren't really in the middle of it like we were, but they came up with a plan, a critical path plan, what equipment, what processes we need to get online, and what order to be able to get right back up in compliance with our permit. So that was really impressive. We get a lot of new equipment out of it, but I always kid, I would not recommend that to anyone as a renewal and replacement program. It was very stressful. Anyhow, so the planning, going again really in early 2011, the first thing we did was we looked at our existing process to see if there were ways we could optimize that to remove nitrogen and phosphorus to the levels of the new permit. And what we found was we could meet our new nitrogen permit with some optimizing of the process through chemical addition and improved mixing in the aeration basins. And also, we determined that we could probably meet the 5 milligram per liter limit at some point with some reconfiguring of those basins, installing baffles in different places to create more or less aerobic and anoxic zones. So we didn't really need to do anything with nitrogen. But we did some jar testing. We took a look at what was coming in as far as wastewater, and we determined that we really wouldn't be able to meet the phosphorus limit without some type of new process. So we went through a process of identifying some technologies to evaluate. Started that in June. And just for your information, and for Angelo and Art's information, when we did this wastewater testing, this jar testing, we basically wanted to determine what portion of that phosphorus was non-reactive or that we would never be able to remove. Because a lot of, certainly the particulate phosphorus, easy to remove with all the technologies that are out there now. The dissolved oxygen and the fine particulates, a little more tricky, but the dissolved organic, so this portion here, we basically consider it non-reactive, and you're never going to be able to remove that with any technologies that we were able to identify out there. So, and just so you can see, on the filtered side, that non-reactive portion, the lowest really you're going to ever see is 0.03 milligrams per liter as an effluent. 0.03. That's it. That's as low as you can go.
That's what you want in your next permit?
No. So here's just some quick schematics of some of the technologies that we piloted. This one here is a 5 micron disc filter. And actually, ironically, we weren't even going to initially pilot test this. Wasn't one that we looked at, but during the delay after the flood, this technology became available. So we decided to pilot the 5 micron disc filter. And this works, these two work a little bit differently. This process, the flow comes in from the outside and goes into the middle. And it's a filtering system. When the pressures get high enough, it calls for a back wash and the solids get taken out. The other process was this 10 micron filter. Here, that's actually almost the opposite. It's an inside out flow. And this one, the manufacturer offered to pilot for free. We weren't going to look at this originally because we didn't think it could do the job. So we said, all right, if you want to pay for it, we'll take a look at it. And then the last was this ballasted flocculation system that Angelo talked a bit about. And that seems to be the choice process for folks. And I can tell you, we looked at the kinds of things we were looking at when we were determining what was going to be the best process. was performance, so how low could it get? The head loss requirements, through the plant, we have some, that's, all related to power, how much power it's gonna take you to pump things around. So power requirements, chemical requirements. We looked at sludge generation, issues with sludge quality. Footprint was something else. We didn't have a lot of room to play around with. Cost, we always look at cost. Staffing, requirements, instrumentation, and how each of these processes dealt with flow variability. And just quickly, we set up the pilot testing, all side by side. They basically bring in a little trailer or a portable unit, and we set them all up side by side. We took our effluent from our secondary clarifiers that got pumped to our spare chlorine contact chamber, so it was available. And then each of the companies tested, ran their processes. We used 2 different types of coagulants, aluminum sulfate alum and ferric chloride, to see which one worked better as far as being able to pull that phosphorus, especially the dissolved phosphorus, out of solution. These things ran for 5 days a week, 8 hours a day, 3 weeks. We did a lot of the testing in-house. We have a Rhode Island Department of Health certified laboratory. I have some excellent microbiologists and chemists on my staff, so that saved us some money. And the one thing we wanted to see was how these processes work under stress, so high flow situations, which we had recently experienced, and slug loads of different pollutants, so slug load of phosphorus or high solids flow. And you mentioned about the sludge. That was definitely an issue for us. We're looking at that. That's probably one of the biggest expense line items we have, power and sludge, after staff, of course. So. Here's a summary of the results. You can see for the 3 different technologies. So the ActiFlow is the Valcid flock system. The disc filter, the 5 micron, and then the mini disc. And you can see in general, the ActiFlow was able to achieve lower effluent limits, minimum of 0.03. That's the lowest. And similar results for both alum and ferric.
Can you go back to that? Why are the influent levels so different for the different treatments?
That's a good question. I think there was some kind of a pre-filter on the ActiFlow. And where the other ones are actually the fabric filters, cloth filters or something, there was no pre-anything. And also, they got to pick their own polymers as well. I don't know if that had an effect, if they, I'm not sure, but that's a good question. And actually, between the 2 types of coagulants, alum and ferric, we would prefer to deal with alum and ferric. Ferric's pretty nasty stuff, and there's a lot of OSHA kinds of things you get involved with ferric.
So those percent removals on the same slide, it looks like the aqua aerobic does the greatest percent removal, right?
I don't think those are percents.
No, those are milligrams, those are concentrations, but I see what you're saying, yeah. It goes from, and I think that's the whole idea, is it's a fabric filter, it's an actual physical filter. So it does really do quite a good job if there's a high concentration of solids in the influent.
Did you say you like the alum better than the ferric?
Absolutely. The ferric is pretty nasty. Just some quick comparisons. We had this similar engineers. We had as West Warwick, so we kind of worked together. And we took a look. We have similar flows, similar wastewater characteristics, so we kind of shared data. They also piloted the ActiFlow process, and then they also piloted this Densideg process. which it's called a COMAD process. Do you know much about that Densitec process? No. In any event, we took a look at all of these things, and you can take a quick look at some of the things we started tracking. And dosage of polymer, that's a cost. We wanted to see we wanted to kind of get a sense of the chemical costs and the other costs involved, operations and maintenance costs involved in the process, not just the capital costs.
Now, did all of those use different polymers?
Did all of them use what?
Were they the same polymer or different polymers?
They got to choose their polymers, so, but we did, here's the facilities plan right there. And that's all documented, and, that would have been something we could also have had input on, I would say. So basically what we found was that the ballasted flux systems have more consistent removal than the filters.
Is there any reason why the Densitec process produces a much thicker sludge than the other ones? I mean, that's a 2.8% solids.
Sure. That's a good question. We didn't pilot it. I'm not as familiar with the Densitec process. I understand it's some type of a COMAD, not very different than ballasted flocculations. It's kind of similar, but that's a good question. So obviously we stayed away from that one. But in general, the ballasted flux systems had slightly lower chemical usage than some of the other processes like that. And again, the disposal of sludge, the sludge concentration, it's not something to overlook. It's, like I said, our second biggest expense. So we're going to be focused on that going forward. And then I spoke to the different kinds of phosphorus, the speciations of the different phosphorus, and just to show you, again, the non-reactive portion, even though in Warwick we were able to get down pretty low, you're never going to be able to get that non-reactive portion to go away. So you're not going to be able to remove that. And it's pretty consistent regardless of the technology. So basically all the technologies that we piloted would allow us to meet our new permit limit of 0.1 milligrams per liter under normal operating conditions. When we stress tested these processes, though, the filters were less reliable. The active flow process, in the end, ended up having the lowest life cycle cost, so the lowest capital plus annual operating and maintenance costs, and the highest probability of allowing us to meet a future permit limit. And again, we have a limit of 0.1. You don't want to just shoot for 0.1. You got to shoot for something lower for a little safety factor. I know my operators don't want to be running right at 0.1. An active flow process seemed to be the one that would allow us to get lower in the future. Again, the non-reactive portion of the phosphorus you're never going to be able to remove. So if we had to, it would be some type of very, very fine membrane filter system we'd have to add on to the end of the phosphorus building. So what happens after that from a project management point of view? So we have to pull that all together in a report. There's our facilities plan right there, chock full of data and engineering analyses and appendices that include all of the data, all the daily sampling that we did for all those pilot processes. Pulled it together in a report, and then we have to have the public hearing to explain what we want to do, what we think it might cost, when we're going to do it. After the public hearing process and the input from all sorts of different affected parties, we submitted to DEM, and then DEM approved it a month later. And then what happened was, because after the flood, we have a levee around the treatment facility, so a berm, an earthen berm, that protects us to the 100-year flood level. Well, we were completely inundated. There's probably like a 400-year flood back in March of 2010. So we had started to look at increasing the height of that levee, and that was running on a sort of a parallel track to this phosphorus process. And as they started to track together, we realized if we could combine those two projects together, you're basically talking about one contractor, one overseeing engineer. There was a lot of potential cost savings. We're going to be digging a hole for a foundation for a new phosphorus process. We could use some of that materials to increase the height of the levee. So we talked to DEM, and they were quite reasonable, and they understood that that made a lot of sense. And really, to install new equipment and processes into a facility that may flood again before you had a chance to raise that protection level really didn't make a lot of sense. So we actually got another 1-year extension, and that's pretty much the best you can hope for when you're dealing with a new permit, is to buy some extra time. But time's money, so it's a balancing act. And the phosphorus project now is completely designed. The levee project is at about 90% designed. We are on track to go out to bid for this in the spring and complete construction in May of 2016. The other piece of this, of course, is the funding. And as Angelo mentioned, we spent a lovely evening last night at a city council meeting. But we're successful in getting the city council to approve basically $56 million in new sewer bonding, 21 million of which will go to this project here at the treatment facility, and the rest will be to expand sewers over the course of the next 20 years. So I think that's pretty much it that I had.
Questions?
The height of the
Say.
levee, how much, what size storm will that keep you from flooding?
So we ran some numbers. We did a risk-benefit calculation. To get to the 500-year level of protection, it's going to cost us like $5 million. To save $14 million in damages, and me ended up in Butler, we decided that was worth that expense. And we're hoping to get a grant from FEMA for a 75% match on that. The levee's got to be increased almost 7 feet. So this is going to be a really interesting project. In some areas where it comes, the back of the plant, it comes right up against the secondary clarifiers. We can't, there's no room really to change the slope of that. We're going to have to use some type of PVC sheeting or something that we're going to drive into the levee to increase the height. So it'll be a flood wall, they call it. So some areas will have a flood wall, and some areas will be able to use earth to increase the height. That's cheaper, obviously, than the flood wall. So where we can use earthen levee, we will, and where we have to use a flood wall, that's what we'll do. But definitely worth the
What are you going
cost.
to do along 95? 7 feet there too?
95 is actually at the 500-year flood level. There is a little portion on our access road that we're going to have to put a little wall over there, but no, that's actually the higher end of the plant, and 95 itself is at the 500-year. So that's why there's only a levee around 3 sides of the treatment facility, because that other side is 95. But that was shut down as well. That got completely flooded out. Most of it coming from the treatment plant, pushing out to the highway. So if we can keep it out of the treatment plant, we'll probably keep the highway open as well.
Other questions? Thank you. Let's thank the speaker, please.
You guys heard me, AECOM siren, right?
No, we're good.
All right. They really are pretty cool.
It's yours. No, I didn't. And our final speaker is from East Greenwich, and Mike Pacillo is the. Are you an executive director too?
No, I'm a plan manager.
Okay, so we have a plan manager. I think it's equivalent to an executive director though, so maybe we should promote him here.
I'll take it.
He's probably a little more hands-on than.
Yeah.
And he's been running the plant for a number of years. We've had plant trips to his plant to see the systems that he's got for tertiary treatment. And I think he was lucky, he got money for tertiary treatment a number of years ago. And let's go.
I change the slide on this
Okay.
when it comes time.
Here.
Yeah. Gotcha. Good afternoon. I am Mike Pacillo, as the slide says here. I'm the wastewater superintendent for the town of East Greenwich. I'll tell you a story about the 2010 floods. Janine and I play golf together on occasion, and whenever we get together to play golf, she'll say, how's your plant running? And I say the same thing almost every time. I say, it's putting out holy water. During the floods of 2010, East Greenwich got hit with them too, but the analogy I like to give is I had stuff going out the doors, Janine had it going in the doors. So she had it much worse than we did, although we did not have it very, very nice. During that time, we got ours under control fairly quickly in a couple days, 3 days. So I thought I'd be a nice guy, and I figured I'd call West Warwick, and I got their answering machine. They were underwater too, and I asked if they would give them canoe rides as a tour of their facility. They didn't like that much. But I called Janine up to offer any assistance that we could give to Warwick, which, there's only 4 of us in East Greenwich, so what we could do, maybe get them coffee or something, I don't know what. And she was at the command center, was it? When I called, and I got a hold of her at the command center, and the phone picks up, and I'll edit what she said to me was something to the effect of, I don't want to hear about your damn holy water now. So, anyways, East Greenwich is, we've had a treatment plant in place. Let me back up. Let me just tell you the hierarchy of the town. The town manager is Thomas Coyle. We're a town-managed style of government with a town council. We have no mayor. My director, DPW director, Joe Duart, he is a URI graduate, by the way, and it is me. Our most recent upgrade, which is our denitrification facility, was done by Ty and Bond Engineering. They're very, very good engineers. They were selected because they're the ones that did the upgrade in 1988. The most recent, not the most recent upgrade before that. J.L. Marshall and Sons was a general contractor, which was like deja vu all over again because they're also the ones that built the plant in 1988 too. And the system supplier for the denitrification system was Severn Trent Services. Give you a little bit on timelines, a little bit of the history. This is our denitrification building right here. I'll give you a little bit about the history of the treatment facility itself, which goes back quite a ways, and the nitrogen removal system, and the performance and some of the operational experiences we've had. Some timelines for you. 1927 is when the original plant was built. That's 15 years after the Titanic took its fateful voyage. So it's been around a while. The initial plant was an Imhoff tank with rapid infiltration beds following it. In 1958, which is the year I was born, They upgraded to trickling filter. Yeah, that gives me, I'll tell you how old I am. I am old. They upgraded to a trickling filter. That lasted well until right around here, they put in an interceptor line that went out to the western part of town to take in some industries and a dairy. Once that happened, the treatment plant did not perform well and needed to be upgraded. Right about there, 1988, 89, a new 1.24 MGD RBC facility was built. RBCs being rotating biological contactors. Now, slightly before that, they put in new secondary clarifiers, which were pretty large for the 1.24 flow. And the thought behind that was, we'll at least clean it up a little bit until the RBCs get built. So basically, everything that was built from here to here was demolished, and this was put in 1989. Then we went out to facilities plan. Right around here, we put a new ultraviolet light system in for effluent disinfection, and right here, the nitrogen upgrade, removal upgrades. You can see the preliminary final design was done here somewhere. Construction between 2004 and 2006, which 2006, we started performance testing and went operation. And we've been operational ever since. This is the old plant. And I mean the old plant. These are rapid infiltration. These pictures were taken back in 1920-something. This, you can see right here, this is Greenwich Cove here, and these are the rapid infiltration basins right next door to it. You can't see it too well in this picture, but maybe in the next one you can. Yes. Right here, this is a shot across the rapid infiltration basin, and these are the Imhoff tanks right here. Now, all the Imhoff tank is, I don't know if you guys ever looked at them or heard about them or anything. It's just like it's a primary clarifier with a false bottom in it. And what happens is the sludge goes down into the bottom and it goes into its second chamber where it sits there and stews and becomes anoxic and it anaerobically digests, in theory. In actuality, it becomes septic and stinks like hell. So the effluent from these Imhoff tanks would flow out into these rapid infiltration beds where this was all sand and these were just splash plates, basically, to distribute the Imhoff tank effluent onto the rapid infiltration beds where they sink down and just percolate out. Real good technology. This is just another view of it. You can see one of them in use here. This one's in total use. And believe it or not, up in a few years back, I've been with East Greenwich for 10 years now, but I want to say there was a plant in Connecticut using this technology as late as the 1990s. What's that? Using the same technology as late as the 1990s. Just another view of it. And this shows you how they're burned up and they're just going over. This building right here, believe it or not, is still around. And if you look over here is the pump house. Now this pump house would take all the waste from what's called the Water Street system and bring it in and just pump it up to the Imhoff tank, which is over here. See this little building right here? Keep this in mind. This is going to come into play a little bit later in the presentation, this little building right here. This is what it looks like today. We have primary clarifier right here. We have actually headworks right here, which you really can't see. Well, this is after the first upgrade in 1989. Primary clarifier, headworks up here where we have a bar rack, two primary clarifiers, a pump chamber here, and this section right here, although it looks pretty short, it's quite long just by the angle of the camera. This area right here is where the RBCs are. That's my office right there, so I get to look out on pretty Greenwich Cove all the time. This is the Water Street pump station that took in all of that flow. We take in, there's three main tributary lines that come into our treatment plant. There's the Water Street line, which takes everything in like 1/3 of the downtown section down to the water and brings it over here. It's pumped up. The second one is what's called the London Street Siphon, which kind of takes in the other third, other part of the downtown, brings it down. And then there's the other one, the Hunts River Interceptor, which goes all the way up to Route 2 and takes in everything on the outer reaches of East Greenwich and brings it to the treatment plant. Right now, the town council, not right now, but back in the late 90s, made a decision to sewer everything east of Route 2 in East Greenwich. And they pretty much done it at one hell of a price tag, I might add. Now, after the nitrogen removal upgrade, okay, you can't see over here, but that's where the UV unit is. After the nitrogen removal upgrade, you can see they put this as the nitrogen removal facility right here. Took away my view. My view can look over here, but I can't say I look out into a brick building now. One of the things that we are very concerned about in East Greenwich is historic perspective. So the architecture for the buildings had to be, historically accurate, and we use special kind of bricks. Yeah.
I go back a moment when you said you had everything sewered from that point. Do you know what the assessment costs for the homeowners were?
Not what you charged them.
Not as bad as they are in Warwick, I can tell you that.
That's what they cost.
They have a special formula. As far as what, every project that we do, let's say we're going to sewer this room, for example, may cost $1 million to sewer this room, whereas the room next door will be $2 million for whatever reason, digging conditions or whatever. What happens is each project is assessed separately. In other words, your sewers for this room, your assessment may be a lot less than the guy next door, on the next project that we do, or vice versa. An example that we have the Sun Valley neighborhood, which had to be sewered, but it also has Camp Fogarty, the National Guard. So the government kicked in $1 million for the sewering. So their assessments were a lot lower than, the next one that we did, which was, I think, Queens Grant, which was much higher. I don't know the exact numbers, they vary. They are starting to be brought down. I can tell you this, 2/3 of our budget, we have a $3 million budget, and a good 2/3 of it goes for debt retirement. And that's for all the sewer expansion that we did, and this here. Here it is, and this right here. 2/3 of our budget just goes for the debt retirement on those two things, sewer expansion and that. Now, we supplement the sewer assessments. You guys do in Warwick too, don't you?
The users subsidize it to some
Yeah,
extent.
it's user subsidized. Yeah, we do the same thing in East Greenwich. Back in 2001, I believe it was right after the fish kill, Angela, somewhere like that, something like that. We entered into a consent agreement with DEM for a monthly average total nitrogen limit of 5 milligrams per liter. The period of time that we were supposed to meet that 5 was June 1st to October 31st, with a March 2006 construction completion, with May 29th permit compliance. Then when we got right in the middle of it, they changed their mind and made it May 1st. And that created a little bit of trouble, to say the least, a little bit of sweating and scaredness, if that is such a word.
It is in our business.
What's that?
It is in our business.
Yeah, and it just created a lot of unrest, we'll say. And the reason for that being was the nitrogen building and nitrogen removal system that we had was based on temperature that you would typically find, May 1st, not in April 1st, water temperature. Now, was it that much radically different? No, but the engineers got all excited about that and everything. One thing we're finding in East Greenwich is we nitrify. We have no problem with that. That is not an issue in East Greenwich, and I'm not exactly sure why that is. I think it's a function of us having a fixed film growth system secondary. I think that's what it's a function of, as opposed to an activated sludge system or a suspended growth system like most everybody else has. But that's just my years of experience talking and no scientific basis to back it up. Again, this is our system right here. Headworks, primary clarifiers, RBC units, we have 8 of them. This is kind of, we're going through an upgrade, we're going out for design on an upgrade for these things right now because they basically outlived their useful life. And we have clariflocculators. We don't have secondary clarifiers, we have clariflocculators, which is a little bit different. Now, in actuality, they're clarifiers, okay? But they're called clariflocculators because at one point in time, that trickling filter effluent I was telling you about earlier, they were going to treat it with polymer and try to let, drop more solids out and get a better quality effluent until these things went online. That was the intent behind it. The actuality behind it was it made no difference whatsoever. They did a study and they found it did no difference. The addition of polymer really didn't help and didn't help clarify anything. So then it goes directly to the UV. Back before we put this in, it went directly to the UV disinfection system. Now, I can speak with a lot of years of experience and say the people that supplied this UV disinfection system are the worst vendor I've ever had to deal with in 35 years, bar none. There is no second place. They were the absolute worst. Unresponsive, arrogant, I can give you a million different negative words to describe it. The people that supplied this were the best vendor I've dealt with in 35 years. Absolutely the polar opposite of these people here that did this. Now, this system here, does it kill fecal coliform? Does it kill enterococcus? Yes, it does. But what you have to go through to get to that point, you get agita, to say you get agita would be an understatement. These people have a voicemail I left them one time and they actually circulated it through their entire company because I went kind of ballistic on them. And that was the running joke that don't let the cello call you up at their company. The nitrogen removal system that got tacked on in the middle. Now, in 2020 hindsight, we probably should have put this in before we put in the UV system. Because the quality of effluent that gives it, you heard me talk about holy water, the quality of effluent that this gives you is much more conducive to a UV system than secondary effluent is, okay? Basically, the secondary effluent leaves the secondary clarifiers and goes to an influent wet well, influent being influent to this nitrification process, secondary effluent, and gets pumped through any of three BAF units, which is biologically aerated filters. These BAF units have sand media in them, and the water is injected up along with air. Right around here, we add magnesium hydroxide as an alkalinity adjuster to raise the alkalinity. By raising the pH, adding alkalinity, we keep the bacteria in here healthy. Because the bacteria in here are the Nitrosomonas and Nitrobacter, who will consume alkalinity when they're conducting nitrification. They'll consume alkalinity, turn the water acid, and kill themselves. Kind of dumb like that. So what happens is these upflow filters, they consume the alkalinity, flow out, we've got a fully nitrified process. We add methanol. Now it's kind of foolish, you explain this to a novice in this business and say, yeah, we took all the carbon out over here. So we took all the carbonaceous BOD out of the waste stream. So we got this really good non-carbon effluent going here, and all it's got left in is ammonia. So we go and we convert the ammonia to nitrate here, and then we're going over here to get rid of the nitrate, and we're going to add carbon to it. Makes a lot of sense, but it works. These right here are downflow filters. They're downflow denitrification filters. And what happens in these filters is it's just a sand filter that drains down through and goes to a clear well. The clear well, in turn, is used for backwashes and bumping. Now I'll get into what the difference between the two is. Backwashes, all are pumped to the mud well, and that's returned to the influent side, the head of the treatment plant. Very, very fine sludge, I might add. It's like feathers. There's really not much to it. Dirty water. This is just some pictures of this is the BAF tanks poured down. This is what they look like when they're operational because of the air being added, so you'll get a little bit of foam on them. The water flows up from down under and flows over this and down. You can see these tubes, these stand tubes here. It flows down here into the DNF tanks right here. Typical operations, we start the system for nitrification on 4/1, or April 1st of every year. Now, in actuality, we can start it and get it going most any time. We run it as a sand filter year round, just about. We don't have to, but we do. And then about around a week and a half, we have to play it by ear. We start up the methanol addition around a week and a half into it. So we get, compliance of 5 milligrams per liter by May 1st. Since we've started it during season, this is what our average has been right here, 3.8 milligrams per liter total nitrogen to start, which is a pretty good number. Now, one of the things you have to be concerned about with methanol is it has a BOD of 497,000 milligrams per liter. So when you start adding methanol to a waste stream that doesn't have any, the methanol consuming bacteria haven't started to promulgate yet, you gotta be very careful on how you dose it, because you can knock your BOD limit out of the water when you do that. So you have to be very, very careful with it. We started up very, very slowly, and we're probably a little more cautious than we have to be, but other than that, I don't really need to have, the state yelling at me about blowing my BOD number. Just to get on the process schematic, you can see we've got 3 of each unit, and we use all 3. The reason for that being is it doesn't cost anything to run all 3 units. And the second reason is it's not real easy to start one of these things up and drain it, shut it down, drain it, and start it up again and expect to get good results out of an empty tank. It's just, you're much better off, because a lot of the bacterial action is in the media itself. And when you drain it, you kill all the media, all the bacterial action. So, anyways, the backwashes again go to the mud well, and the mud well discharges to the head of the plant. Permit compliance period, methanol addition, alkalinity adjustment, backwashes, and bumping. A bump is basically a mini backwash. Okay, what happens is we have to bump the BAF units periodically because the media gets bound together. So by blowing tremendous amounts of air and water through it real quickly for a very short period of time, you loosen it all up, and the upflow is much easier. On the downflow filters, the DNF filters, are something that a really strange thing happens. And if you didn't sit there and watch it happen, you wouldn't believe it happens. Because you have denitrifying bacteria in a sand medium, well, the denitrifying bacteria are taking nitrate and they're reducing it ultimately down to nitrogen, which is a gas. So what happens is that gas comes out of solution, but it stays trapped in the medium. So what happens now is the water can't percolate down through the medium because they got all these trapped gas bubbles in there. And so the levels of that tank start to go up and up and up and up, and pretty soon, the system is kind of stupid. It says high level means backwash. You don't need backwash, you need to bump it. So what happens is a little bit of high pressure, high volume water gets introduced to the bottom of those filters just to flood them just for a couple seconds. I think it's 90 seconds we run our pumps for. And that loosens up all that trapped nitrogen, and the levels drop like stones. As far as bumping, we do those periodically throughout the day. And what it amounts to right now is we do about 1 to 2 backwashes per unit per day. What I mean by per unit is we might backwash 2 BAF units and 1 DNF unit in a day. Or we might backwash 2 DNF units and 1 BAF unit during the day. So that's what we do. During November through April, we had a little bit of magnesium hydroxide. And the reason we do that is we like the effects that it gives at the whole treatment plant. Sweetens the whole thing up, jacks pH up a little bit. and we take the methanol right out. Don't even use it. We operate all of them year-round, and as far as backwashing, bumping, very, very little during the off-season. The SCADA system, all it does is allow us for control and supervised control and data acquisition. It's a good trivia question, what it stands for. All it does allow us to control from the main building, treatment plant building, or the nitrogen removal facility, all the innards of the system. The pumps, the valves, the motors. You can see all these motors, valves over here. Up here are motorized. We use dry pit submersible pumps on the influent. All our pumps are dry pit submersible. And the reason for that being is I required that back when I was first got there because number one, I know these pumps very well. And number two, if this building ever floods, the last thing I want to do is have to replace pumps. So we're prepared for some flooding, if nothing else. Now here's the Holy Grail, the engineers up there. These are the original mag pumps. If you can find a chemical that has is number one, safe to handle, it's not going to burn you to death, okay? Is as economical as magnesium hydroxide, okay? And is not a slurry like magnesium hydroxide is. You got the Holy Grail. You can sell it to anybody and they will buy it because these are the original magnesium hydroxide pumps. I had an operator cleaning these things 3 times a day. 3 times a day, he had to go down and clean these. The reason for this being, not the pumps that are bad, they were the engineers that sized them basically say a little's good, a lot's better. Now one of the things, in wastewater, that's usually a good thing, right? But when it comes to chemical feed systems, that's not a good thing. Because what happens is the magnesium hydroxide is a slurry, and it will settle out. And if you don't move that stuff fast through the piping, it's going to plug up all the piping. You're going to be back flushing it, until you can't back flush anymore. What we were able to do is we reduced the size of the piping. We pull these pumps right out, and we reduced the size of the piping, and we changed the pumps to peristaltic pumps, which were more suitable to our needs as far as the gallons per minute or gallons per hour that we had to pump. Now, if somebody asked me how many gallons per hour were the other ones, how much of these, I don't remember. All I know is that we very seldom have to clean these, maybe once a week. We have to flush them. I mean, we give them a little courtesy flush once a day, but we don't have to flush these ever. I mean, not ever, but once a week we tear them apart and just make sure that they're nice and clean on the insides and everything else. And that's a big deal for, this stuff is nasty stuff. It's milk of magnesium. Magnesium hydroxide is milk of magnesium, it's the same thing. One's food grade, one's not. But it's a very good alkalinity adjuster. The methanol addition system, this tank right here in the foreground, in the background, that's our methanol storage tank, and this is our methanol day tank. This building here houses the methanol feed pumps. In here, a transfer pump transfers from the storage tank to the day tank. And in here, a pump, one of 2 pumps, feeds methanol into this building, into the BAF effluent, so we have a carbon source for denitrification. Because the denitrifying bacteria can't live without a carbon source. And this is the brains of the unit, the ChemScan unit. What this ChemScan unit does is it paces the methanol, and it also, we've got it now pacing the blowers, okay, for the operation of the plant. And I'll get into that in a little bit. But what this does is this takes a sample periodically, and I don't know the exact sample times you've got it set for, and it reads the effluent nitrate of the BAF unit. And what it does is it tells the methanol pump, okay, you got X amount of nitrates going out of the BAF, you've got to add this amount of methanol, okay, to get that number down to an acceptable level. Now what we've been able to do, back to the next one, is the process air blowers. These are the process air blowers. These blowers right here, there's 4 of them. You can see they put one of the things my guy is very good about is saving time. So he takes the air filters we have to change once a week, and he puts them right out there so that we have the air filters. We take these little doors off and just change the air filters on them probably about once a month or something like that. These are 30 horsepower each, and they used to run 24/7. Now they only run periodically, it might run 15 minutes an hour. Okay? These ones over here, that's them. These are 125 horsepower. These things start up, they're loud and they draw electricity like you wouldn't believe. These units right here, if you take these doors off and you start them up, they'll knock the fillings out of your teeth, they're so loud. As far as costs go, or impacts, I have a dedicated tertiary operator during the summertime. He works in that building only, and he takes care of the tertiary treatment system, and he takes care of the UV unit. Average cost is magnesium hydroxide. Now this varies. We've been able to trim this down substantially since I wrote these slides. Average yearly cost about $13,000. Yeah, maybe a little less than that. Methanol use, $14,000. I will tell you this, what we've been able to trim it down to right now is, let's see, that's $27,000. Our chemical cost is around $20,000 right now. So we'll be able to knock $7,000 off that. Additional power consumption, we have 320 horsepower loaders that used to operate 24 hours a day. Now we got them down to about 10 hours a day, alternating. And the way we did that is we did it through the ChemScan. And Severn Trent, the system supplier, wanted, for lack of a better term, a guinea pig. Their original intent was to, instead of taking basically what they're, without getting into the chemistry and everything involved in it, what their original intent was to find a way, instead of taking ammonia and going to nitrite into nitrate and then reducing it down to nitrogen. This is a pretty cool idea when you think about it. They said, why are we taking it all the way to nitrate? Why don't we just take it to nitrite and then back down? Okay? That's a pretty cool idea. And I sat there and I said, stupid, why didn't I think of that? Why didn't anybody else think of that? Really? Well, it's not as easy as it sounds, number one. But what we were able to do, they came in and piloted it, and we tried it during the off, when we're not permitted for nitrogen. But what we found was, we weren't able to do it because those bacteria are really a pain to get. There was a lot of roadblocks to getting to that point. But we did find we don't have to operate these blowers 24 hours a day. And we'll also get denitrification in our bath units by doing this. We actually get a little bit of denitrification in our bath units, which takes off strain off our DNF units. Okay? We also have two 15 horsepower influent pumps that operate 24 hours a day. That's kind of erroneous. One here 15 horsepower pump operates 24 hours a day. The other one kicks on periodically. We have additional backwater and mud well pumps. Again, startup in April for May. Startup magnesium hydroxide system, methanol system. That's another just view of the methanol system here. What happens when the bugs die? Back in the old days, back in 2008, we were in the middle of an I&I reduction program, and we found one sewer line that had a root problem in it. And as part of the I&I reduction program, we had to de-root the sewer, which we meant vapor rooting. So the vapor rooter guy came in, and that's a trade name, and I don't want to know if I want to use it or not. But I think it was vapor rooter. It was one of those rooter companies that comes in and puts a chemical in the sewer. And they assured us that it was 100% safe, it was not going to harm anything. And they just treated 200 feet of sewer. And what the stuff does is they put it in a sewer jet, they put it in a tank of a sewer jet, a very small amount, and it creates a foam in the sewer. And the foam attaches to the roots and kills them. It's an herbicide. And the foam attaches to the roots in the sewer, and it kills them dead, and then you go back with a cutter and they snap right off. They're dead. Well, about 6 hours after they applied the root killer, You go in to look at our trend charts, all of a sudden the nitrate was up here and it went bang, right to nothing. You know, everything went to pieces. That root kill was so toxic, it killed all the nitrifying bacteria. It killed the denitrifying bacteria. And just completely destroyed our system. That tells you how, because our secondary system was fine. It made it through the secondary system, and we didn't have any really degrading of effluent from the secondary level as far as BOD and TSS. Again, I think that's a function of being an RBC process too. But the Nitrosomonas and Nitrobacter took a beating, and the denitrophilias took a beating. And but through some hard work by one of the guys that works for me, who is a URI grad, I will add, we were able to recover in 1 week without no receding. He really stuck with it. He did a lot of stuff on his own. Worked a lot of overtime too, but he did a lot of stuff on his own. He did a hell of a job getting that thing squared away. Then we got old school nitrogen removal. That's back in the good old days. Right? So that's not me, by the way. That's a little before my time. And one final picture. If anyone needs to email me, got any questions about the East Greenwich plant, feel free to do so. Want to take a tour, give me a call, send me an email, shoot me an email. I'll be more than glad to take you around. Any questions? No. Cool.
Actually, I got one, Mike.
Yeah.
The BAS systems that I've seen have been open. How come you have yours inside of a building?
Because
And
we're
what
in
are
a
the
historic
impacts,
district and we're in East Greenwich. We can't have those
so
kinds
it's
of
really
things
for
outside.
this
Yes. Our total cost for this building right here was, this building alone was $7.53 million. Now you see this wall right here? That wall is a beautiful architectural wall. It was put up for one reason and one reason only. So if you're out in your boat, you wouldn't see the methanol tank. Okay, that's a slate roof. Those are slate roofs. All of these are slate roofs, by the way. I'll tell you a good story. Back in 1988, when we were building this thing, a guy pulled up at the recreation garage and wanted to know how much the units were going for in this building. That's a true story.
Wow.
The guy said, "Go see the guy upstairs. I'm sure he'll sell you one."
Oh, yeah.
I would have sold him one. Hell yeah. But you can see we're right in downtown historic, East Greenwich with all the, the Revolution, Nathaniel Green, and all of that stuff. And, the Bonham Armory's over here, and the Kentish Gardens over here, and the Town Hall's over here. It's all historic architecture. So we had to do something that blended in really nice. And I think we accomplished that. I mean, it's a really beautiful facility.
What do you have for odor control?
What's that?
What do you have for odor control?
We don't.
You know?
Nope. The best thing we have for odor control is we don't handle sludge. Get rid of it. I've found that, and this has just been my experience, odors are caused by a few things. Number one, seepage. We don't take seepage. Okay? When I drive by Warwick and I smell something,
It's
no, it's not the
rancid.
plant, it's the septic, right? Septic tank trucks. And let's just think about the logic behind it. You flush your toilet, if you have a sewered house, you flush your toilet, within 12 to 13 hours, that sewage is being treated at the treatment plant. Okay? You got a septic tank, you flush your toilet, it goes in a hole in the ground and festers for 3 years. What do you think's gonna smell better? I mean, really, and it's 3 years if you clean it every 3 years. So these guys go and they fill up a 3,000-gallon tank truck full of septage, and then they release it into an aerobic system where it gets agitated and gets gas stripped, air stripped, and everything else. That's where all the odors come from. Another thing that you find, low pH will cause odors. One of the things we do, and we do it by design, I guess. We do it by design, our design. We add a little bit of mag to this building right here that freshens up all the waste stream going through it, keeps the pH up around 7. Just a little bit, not much. And it also gives alkalinity through the process, because what we can do by doing that is over there where the RBC units are, is sometimes we get a little bit of nitrification on RBCs too. So we're able to do that. Another thing is, we don't have sludge handling equipment. Our sludge handling takes place right there. A sludge truck drives up, we put a pipe right inside his truck, we turn the pump on, he's done, he leaves, we shut the pump off before he leaves, obviously, and that's it. So those are the things that cause odors, really. Another thing, we have a 5-year cleaning plan on our collection system. Nothing can really get too stagnant in the collection system. We keep the stuff coming. We clean all wet wells at least once a year. Just housekeeping stuff, you know? We do have, don't get me wrong, there is an old odor control system that was built in 1988. It was an ozone generator, which was probably the stupidest place to put an ozone generator you could at a treatment plant, because back in those days, you had to have ultra dry air to run it. And if you look, I mean, we're right on the water. We've got 2 belt presses in this room right up here, you know, squeezing water out of sludge. And we're going to take that wet water and we're going to hit it with ozone, generate ozone out of the air in this building. Oh, yeah, that's going to work. So we don't use the ozone generator. Now, that being said, we have not had an odor complaint in over 10 years. So it's easy to minimize, you know, odors and everything, but the proof is in the pudding. We haven't had one in 10 years. Yes, Andrew?
One thing I forgot to mention makes it interesting for everybody is federal rules prohibit permits for being more than 5 years. So, you know, as we've been talking about, by the time you issue a permit, go through the negotiations, get something designed and built, 99% of the time, your permit expired either before you finished or right after. And sometimes we're allowed to sort of let them sit for a few years if there's no new information, no likely changes. But the Clean Water Act has lots of opportunities for lawsuits, and so the EPA's been pressured and pressuring the states to keep the backlog of expired permits down. Sometimes there's new information we need to deal with, but unfortunately we've been in these cycles where we either no sooner get the plant finished or it's almost done, and we're back having these conversations. But I'm sort of hoping that we're in a stage.
I was going to say, is this a nice way of telling me something?
See, I thought it was a conspiracy of engineers and construction
It's
guys.
a nice way of telling me something. Oh, God. Not again.
Well, when the governor was first
Keep the
elected and he
engineers
came around and jobs was one of the things, I said, well, I'm doing my part. I'm putting engineers to work, construction workers, but it falls on the back of municipalities, so that wasn't quite what he had in mind. So.
Now, one of the operational problems, I'm glad you jogged my memory. I don't know how you did it, but you did it. Remember I was talking about that little pump house I said come into play? Well, one of the things we found, we replaced the Water Street sewer line. We did an I&I study. And the I&I study said there's no infiltration to speak of on the Water Street sewer line. And I sat there and I went, but the thing's made out of cast iron, it's underwater, groundwater table's above it, it's made out of cast iron, it was put in 1927. Okay. 1, 2, and 1 plus 1 plus 1 equals 3. Okay, that's just the way I think. And they said, no, there's no infiltration, nothing to worry about. Well, we're going to replace it anyways because it was actually went uphill in a couple spots and stuff doesn't flow down uphill very well. So we went and replaced it. What they didn't do is, what we decided to do is abandon the sewer line that was running along the ocean here, or around the cove, and we moved it inland up here. We actually, it actually saved some money on the project because we didn't have to deal with too much coastal resources and all of that stuff because we pushed it inward. But we actually had to dig a lot deeper. Well, they started digging, and they ran into water. And I said, well, surprise, surprise. Here's the cove, here's the, where do you think the water level is going to be? Right about there. Okay? The engineer and me, right? So they dig the hole, they run into water, so they get pumps to pump the water down so that they can get the trench dry enough to lay pipe, and the pumps aren't keeping up with it. So they bring in more pumps. They're not keeping up with it. So they said, that's it, we're gonna double the amount of pumps. They brought that in. That barely kept up with it, so they brought in more pumps. Meanwhile, they got pumps coming all the way down the street and everything else to get this water in. One of these old timers that retired about 1988, 89, I run into him at Dunkin' Donuts. And he says, you guys got some water in that hole over there, huh? I says, yeah. He goes, did anybody tell you about the artesian well? I went, what? Well, that picture, that little shed I was talking about, that was an artesian well. There's a spring that ran through there, a very high volume spring. And what they used to do back in the old days is they used to use the water from that artesian well to provide chase water for the chlorine. There was an abundant amount of water, a spring right there. Nobody knew about it. When they knocked when they knocked it down, they just said, the hell with it. That was it. That's where they're running all the water. We put that sewer line in, about 150,000 gallons of I&I, bye-bye. Okay? And that's a very substantial amount of our flow.
Absolutely.
But there's no I&I there. At least that's what I was told. But what they did was, and the reason they said that, is they stopped their I&I calculations over here on Water Street. And they were right. The Water Street line wasn't leaking. From there back, but from there forward, it certainly was. And that's where we, you see our flows now, they're up, they were up here, and all of a sudden you see, boom, they're down here now. And, we're talking a substantial reduction in flow. One of the other things that we were able to pull off back in the old days, when I say old days, I want to say about 14 years ago, I wasn't there for it, is we got a capacity, the capacity of the plant was changed from 1.24 to 1.7 million gallons a day. That was done, this is part of the reason for that, right here. We built that as part of the trade-off of getting that extra capacity. And we were able to do it, but it's a zero-sum game because you can't, the anti-backsliding regulations EPA has, your effluent pounds stays the same, your effluent milligrams per liter stay the same. If your flow goes up, you better drop the milligrams per liter if you want to make the pounds. And we're able to do that without much trouble at all. I mean, we're talking, we get 97, 98% removals. And our effluent's usually single digits. Holy water, right, Janine? Holy.
That's what you tell me.
Yeah.
How many years did you get out of your RBCs?
We've gotten, well, they're still running. But we've gone through damn near every shaft there is. What happens is you got a 4-inch shaft on a thing that, carried 30 tons of media and biomass, and it's rotating 24/7, 365 at a rate of, one revolution every 40 seconds. Doesn't sound like much, but multiply it out over 20 years, and you've literally got millions of revolutions on those shafts, and there's stresses on them, and they will snap. And so what we're doing, we're going to just rip them all out, media, everything, replace them. That's our grand design.
And what are you going to do for your secondary treatment as that's being done?
Well, we'll only do one train at a time. We're only running one train of RBCs right now. So we'll make sure one's running really good and rip out the other ones and put them back online and swap it over to the other ones. Any other questions?
Now, Angelo said that the Greenwich Bay area has high, low oxygen level and high nitrogen or phosphorus. Where does that all come from?
Probably from Angelo.
It's the animals along.
Our effluent nitrogen is around during permit season around 3.8 is what we average out today. Somewhere in that neighborhood. We got pretty good numbers. I looked at a study of the amount of nitrogen going into Greenwich Bay, not Greenwich Cove, but Greenwich Bay. We're a subsidiary. We dump into, this is Greenwich Cove here, and then that dumps into Greenwich Bay. If I was to take all my nitrogen out, and correct me if I'm wrong on it, Angelo, I did this a long time ago. I think the number is, if I took all my nitrogen completely out, and I was putting distilled water on, okay, I could only affect that number by maybe 4 to 5%. That's in Greenwich Bay. Does that correct? Somewhere in there?
Yeah, I don't remember exactly, but I know that, yeah, the main concern with the plan was the cove area that it's in, and the CRMC did a SAM plan, they call it, for Greenwich Bay, and DEM participated in some of that. And actually, I think Dan Urish had done some calculations, and some other URI professors. And I think it was a large percentage of nitrogen coming from septic systems in the watershed.
Yeah.
And I think it was like, I forget the number, but that's, at this point, there was also some debate about the nitrogen load from the upper bay into Greenwich Bay. Frankly, we went back and forth with some people at GSO that had done some calculations. We didn't quite like the way they did it, and they didn't quite like the way we did it. But we thought they were overemphasizing that flux of nitrogen. But at any rate, we're working on substantially reducing any impact that might be coming from the Providence River. We've taken care of this, so really think that it's at this point primarily septic system nitrogen loadings.
And is it the Warwick part of Greenwich
problem?
Cove that has all
definitely.
septic systems?
Yes.
Yeah.
Yeah, Potawatomi is another
Potawatomi.
area. It's actually closer to East Greenwich than Warwick. That's all on septic systems. That's right on the cove.
So can you send all that to East Greenwich?
We were just talking about it. Mike
Sure
said
they
he'll take
can.
it.
No
He said he'll take it.
problem. It'll cost them, but yeah.
But we already paid for fire department.
There you go, there you go.
Is that where you live in Potawatomi?
No.
Oh, all right.
Yeah, one of the problems or interesting thing is a lot of times the areas that need sewers the most are the old on the coast. They were summer cottages on small lots, and then there's a long distance where there's larger lots or very few users. So it ends up costing a lot of money to get out to those locations.
Yeah.
And Potawatomi's one of those where there's a couple of golf courses. There's there's miles where there's very few people to contribute to that cost. And so if it's going to get added to this group of people out at the end, it makes a per user cost much higher. And
Maybe East Greenwich can sell the gray water to the golf course.
yeah, they were.
We're
they did
kicking
look
around
at,
ideas about
there was
reusing
talk
water
about
and
that.
selling it.
and even like a package. Was it possible to have a package plant for the Potawatomi with some kind of irrigation?
Garden Park Golf Course could use some water.
Certainly could. I'd have to go inspect those sprinkler heads on a daily basis, I would think, too.
You'd be close.
You gotta do what you gotta do, right? So,
Last
anyways.
questions? Let's thank our
Thank you.
speaker. That ends the conference, but it was a fantastic conference. I think the three speakers did a really great job. We appreciate the coming. Thank you, Harry.